Hi everyone, Mrs. Basega here, and today we're working on proportional reasoning. Proportional reasoning is a method in which you'll be able to determine the outcome of an equation based on the changes that are made to the variables. And you'll be able to do this all without the hassle of substituting and solving. You may be asking yourself that substituting and solving wasn't that bad, but what if you had a more difficult equation to work with? So in this example, we'll examine the traditional problem-solving method, and I'll show you how proportions makes it better. So let's freeze this for a second. In this picture, two masses are gravitationally attracted to each other. Fg is the force, the gravitational force between them, and it depends on the product of the two masses, how far they are away from each other, and big G, the gravitational constant. But when we go and do our knowns and unknowns, that means we're working with some pretty unwieldy numbers. The gravitational constant is an unwieldy number. It's immensely small. But each of the masses, the Earth and the Sun, are enormous. And so is the distance between them, right? 10 to the 11th meters is enormous. And that means when I go substitute into this equation, that's going to be tricky to work with. So what are we going to do instead? Let's say we change the question up, and the question becomes, what happens to the gravitational force if the sun were twice as massive as the Earth? If the sun were twice as massive, the gravitational force would still apply. But m2, the mass of the sun, would get bigger by 2. That means the entire gravitational force, with some clever distribution, the entire gravitational force is twice as big as before. The 2 at the front of the equation indicates that the gravitational force has increased. So let's break this down step by step. In step number 1, we wrote down the original equation. In step number 2, we substituted the change that was made to the equation. In this case, the sun was twice as massive. Finally, in step 3, we cleverly sort the original equation to the right, leaving any changes to the left. The 2 indicates that the gravitational force increased by 2. So let's try another example. What would happen to the gravitational force if now, instead of being twice as massive, the sun were twice as far away? We write down the original equation. We substitute in twice as much radial distance, so that's 2r squared. And finally, we sort the original equation to the right, being careful of the square in that parentheses there, bud. And that means the gravitational force is 1/4 of the original force. That means it's weaker than it was before, or smaller. We can use it to do many changes at once. So what if the sun were 3 times as massive and the Earth was twice as massive, but that these objects were farther apart than they currently are? Right? Let's say they're 3 times farther apart. We could substitute all of those changes and the steps stay the same. So step 1, write the original equation. Step 2, substitute in m2, the Earth, is twice as massive. m2, the sun, is 3 times as massive. And the distance r is 3 times as great. Sorting everything to the left and right as before, we see there's 2 times 3 over 3 squared, or 2/3 of the original force. That means the gravitational force would be weaker than before, because 2/3 is less than 1. So let's move to a different equation. I think we've exhausted the gravitational force equation. What about the kinetic energy equation? What would happen if I was taking the kinetic energy of a moving object and I just tripled the mass? I'm doing this example because I want you to be careful of your sorting in this problem. Tripling the mass doesn't change that 1/2. I would move the change, the 3, to the left and keep the original equation, 1/2 mv squared, sorted to the right as before. This isn't 3/2 as much kinetic energy. This is 3 times the kinetic energy. Keep the 1/2 with the original equation so that your thing in parentheses on the right is just the original equation, including the 1/2. An object that's 3 times more massive would have 3 times the kinetic energy. And let's finish it off with 2 examples from electricity. Because you could do this with any equation, whether you're familiar with the concepts or not, for now we'll just practice some math. The picture I'm drawing is a capacitor. It's 2 really big parallel plates filled with charge that stores PEC, which is potential energy in a capacitor. Q is the amount of charge that's stored in the capacitor, and V is the voltage of the battery you attach to it. That symbol next to the V is a battery. So the question is, which stores more energy? Twice the charge or twice the voltage? And according to the equation, twice the charge only doubles the energy. But twice the voltage was squared. So that means twice the voltage actually gives 4 times the energy. I did this example because I want you to see that squares have a larger impact on the outcome of an equation than just linear or direct relationships. And the last one is, can I actually use this to find an answer, an actual answer, instead of just proportions? And the answer is yes. Let's say I have a capacitor that stores 5 joules of potential energy. How much more energy would it store if I put 3 times as many batteries? 3 times as many batteries would triple the voltage. So that would be 3 volts squared. Doing my distributive property, I see 3 squared would be 9 times more energy than before. And if before was 5 joules, 9 times more than 5 joules gives me 45 joules. So to solve a proportion problem, you'd first write the original equation, substitute in any changes to the variables, then sort the original equation from the substitutions. If your number that you found is greater than 1, then that quantity has increased. A number less than 1 means your quantity has decreased, all without the hassle of substituting and solving. All right, so let's practice this on our own for a bit. Best of luck.